Okay, so I'm Nagarajan. I'm a postdoc at Microsoft Research India. This is the work that I did with Prateek Jain, who's not able to make it to the conference. So I'll be presenting this work. In the last few years, I've been looking at prediction problems, especially with the focus on modern evaluation metrics that people use. So the goal is that we want to devise algorithms that sort of directly try and optimize the evaluation metric that people are interested in. So far we have looked at binary predictions, multi-class predictions, and so on. So recently we have started looking at multi-label predictions and matrix completion and more in the modern recommender system settings. So this is the work that is one of the first works in that line of research. So if you attended Manik's talk in the morning, so much of the motivation in this talk is sort of shared with what he was talking about in terms of looking at the right evaluation metrics when you want to solve these recommender system problems or multi-label prediction problems. So in the typical item recommendation problem, you are interested in recommending a set of items or labels to a given user or instance. And so in particular in the movie recommender system setting, so what you want to recommend is, let's say, one or a few movies to the user, and you want to be right in the top few items that you present. So this is typically formulated as the collaborative filtering problem, where you get feedback data of users liking movies. So here the rows represent users and the columns represent items of movies, and you want to predict which other movies a given user likes. And often the metrics that you're interested in is precision or recall in the top few entries. So that's the sort of metric that you're interested in. But then if you go to a different domain, for example, in bioinformatics, you might be interested in different metrics. For example, this is a problem that we have looked at in the past, where we are interested in predicting causal genes that cause, in this case, here the rectangular nodes represent diseases and the circular nodes represent genes. And these connections are the biological data that you get from biologists. And we are interested in predicting which genes are responsible for causing which diseases. So for each disease, you want to come up with hopefully a short list of genes that the biologists can then go ahead and do wet lab experiments to do further validation. So in this case, you want to be precise in the top list, but at the same time, you want to make sure that you get most of the relevant genes so that you don't miss out some critical gene and which might stop from developing a good gene therapy. So biologists are often interested in both precision and recall. So you see that often domains dictate the specific type of metrics that you want to use in these recommendation problems. Often this problem is cast as a low-rank matrix completion problem, which is a popular collaborative filtering technique, and in which case you sort of look for solutions with low RMSE. RMSE essentially is sort of the root mean square error, where you want to predict where you want to fill the matrix such that the entries are in some sense close to the original ground truth. But then the problem is that the RMSE, having a low RMSE need not translate to having a, let's say, low precision or low recall in the top few items that you are interested in. So this may not be the right approach that you want to take if you have a sort of different metric in mind, or if the domain tomorrow, if you want to take the solution and apply it to a different domain, for example. More generally, you may also have features associated with users, or in this case, in this Flickr example, here is this image tagging example. So you're given images and a set of tags, and you often get a few tags among, let's say, a million tags, and you want to recommend, or you want to predict more tags for a given image. Again, you're interested in, let's say, metrics such as position at top K, or as Manik was motivating in the morning, you may want to sort of try new metrics such as this propensity scored metrics that Manik talked about. So again, you want an algorithm that would directly optimize such a propensity scored metric for you. But these are some of the state-of-the-art solutions besides the faster XML that Manik talked about. Indrajit presented PD sparse in the morning, and then there was this local embedding-based method, Sleek, presented last year. Many of the existing solutions often target Hamming loss or some sort of a specific loss. Again, those are the losses that you may not be interested when you evaluate these methods, and oftentimes the solutions that you get may not be geared towards optimizing those metrics. So that sort of is the sort of high-level motivation for this talk, is in that we have different prediction problems in collaborative filtering, ranking, recommender systems, multi-label prediction problems. In all these settings, you have, you have lots of missing data, because often you have millions of items or labels, and you have very, very few training examples. And furthermore, you're often interested in complicated metrics. By complicated, I mean these are non-decomposable, crazy functions of quantities like true positives, false positives, and so on. So you can come up with many different performance metrics, and you really want a learning algorithm that sort of handles both of these sort of challenges. One is you want to be able to handle the missing data. At the same time, you want to be able to optimize with respect to the metric that you care about, and say something theoretically interesting, in the sense that you want to be able to say that the solution you present eventually has some sort of a bounded error in the metric that you care about. So this work sort of initiates this line of research agenda, where we want to sort of bridge the gap between the statistical theory, theoretical guarantees you can get, and the sort of demands that the application deployment may pose. So here is a sort of outline of contributions that we have. So one is we sort of develop an approach that sort of targets each of these requirements in a precise manner, in the sense that we sort of handle the missing data, and at the same time take into account the evaluation metric that you care about directly when you actually learn the model. So at the training time, you look at the metric that you want to evaluate, and we also sort of give precise guarantees with respect to the metric that you care about. So that's a sort of the high-level picture of the next few minutes I'm going to present. So this is the problem formulation. So you have n users or instances, users in terms of the movie Netflix movie example I gave, and each user may come up with a set of features. These are some real-valued features, and you have L labels or L movies. And you observe a sort of you have a partially observed label matrix. These are the preferences. These are binary preferences. You have likes and dislikes, or a label is associated or not. So that's the partially observed matrix Y. And you also are given a performance metric. So this performance matrix takes two sets of predictions. So you have a prediction matrix Y, and you have a prediction matrix Y hat, and you have a ground truth matrix Y. And this metric typically is non-decomposable, in the sense that it operates on these entries in a non-decomposable way. You may not be able to write this matrix as sum over ij, some L of yij, comma y hat ij. And then typically you have label noise, in the sense that the ground truth you have may not be exact. It may have some uncertainty, because these are often human labeled or machine labeled. So you model the label noise by some sort of a conditional distribution. So each yij will have some probability of being 1, and some probability of label can be incorrect. So that's modeled by this conditional distribution. And what is the goal? The goal is to learn a model that has bounded generalization error. By generalization error, I mean the error that you measure with respect to this metric that you care about, psi, in expectation. So that's the sort of problem that we want to solve. So we are going to focus our attention on a family of metrics that we have been studying in the past, again in the context of multi-label learning. So these are, so one thing about multi-label learning is that there's no sort of unique way of defining metrics. For example, to the left I have this figure where in the binary classification, if you have a set of predictions given by F and a set of ground truth, the blue vector given by Y, then precision is sort of uniquely defined. It's just the intersection by the number of elements that you predicted as true. But then in multi-label learning, or in a general recommender system setting, you have several ways of defining it. For example, you can do what is called the micro-averaging, where you basically take this entire matrix and string it into a vector and just apply the binary precision metric. Or you can do row-wise, or you can do column-wise. So I can take each label as a binary classification problem and apply the precision function or any other performance metric of your choice, and then take an average over labels. Or you can do the same thing, but you can do it over instances. I can take the predictions for each instances and then take an average over instances. So these are what in the literature people refer to as micro-averaging, macro-averaging, or instance averaging. So we will restrict our attention to these sort of averaged metrics, and the metrics themselves can be sort of these linear fractional metrics, which sort of include most of the interesting metrics that we care about. And I believe Manik's propensity metrics can also be included in this framework, because there is some sort of weighting that you can account, and if you have a model that weights that you have where you have learned the weights, then you can sort of include those propensity scored metrics in this family too. So the algorithm is this. So we first sort of estimate parameter matrix, what we call W hat. This is of the size D by L. So remember, D are the number of features that each user has, and L is the number of labels. So basically, we learn a linear map. This W, to learn this, because you have lots of missing data, we learn this in a sort of constraint formulation, where this constraint is on the nuclear norm of this matrix. So if the ground truth really were to have a small nuclear norm, then you get benefit. But if the ground truth doesn't really have low rank or doesn't really have nuclear norm, then you can still learn a matrix, but you may not have the benefit of using this formulation in some sense. So once you sort of have this parameter matrix, so in the native collaborative, in the basic collaborative filtering setting, this basically boils down to a low rank matrix completion, except for this sort of bound constraint that we have. So once you have this parameter matrix, then you can score all the instance label pairs. It's just a linear. You do an inner product of the features with the corresponding label parameter, and you get these scores. And once you have the binary prediction, once you have the scores, these score values, then you actually try to threshold these score values at a particular number, such that you can turn these scores into predictions and finally evaluate. And basically, that's the output of your system. You want to turn your scores into a prediction. And to actually choose where you want to threshold, you use the metric that you care about. So you apply the evaluation metric, and then choose for a threshold that maximizes this metric. And this is a one-dimensional optimization problem, and on any given training set, there are only going to be a discrete number of choices for your threshold, and you can do it efficiently. So this is one slide on the nature of bounds we have. So one is that the last equation on the slide is sort of the most important one, in the sense that psi star is sort of the best you can do. That's the optimal thing you can do. And psi of y comma y hat is the output of the metric realized by your algorithm. That regret, so that is directly bounded by a quantity. And that quantity, in turn, is essentially bounded by two parameters. One is that L, which is the number of labels, and rank of W star, which is the parameter that you estimate. So what we have to notice is that if the omega denotes the number of observations you have. So as long as you have about L times rank of W star observations, you sort of have a bounded regret. And we can show that this sort of improves over some of the existing results, and it also generalizes some of the known results for matrix completion in the presence of random features, random noise, in particular exponential family noise. So I don't have time to go into the details, but there's apart from the bounds that we have for multi-label setting, this result sort of covers more regret bounds in the general matrix completion problem. So these are some benchmark results. This compares to some of our own work that we did last year, where again we had general performance metrics. We had guarantees for general performance metrics, but then, as I was pointing to, this one will have sort of weaker regret bounds than what we have in this paper. And we tried on benchmark data sets where the number of labels are about the order of thousands, and the dimensionality of the data points is about few 10,000s, I guess about 40,000 or 50,000 in each case. And in many cases, we find that if you actually directly optimize for the F measure, in this case, the vertical axis corresponds to the F measure computed on the test data. So if you actually use the metric that you want to evaluate on, you sort of improve upon what you can do otherwise. So there are some open problems. One is that low rank. This is the first sort of work in this line, in the sense that we want to handle missing data. At the same time, we want to be able to say something useful about the eventual target metric. So low rank matrix completion may not be ideal in the sense that, especially, it will not capture the tail user and tail label behavior. So we may want to move away from this assumption. So one technique is this sort of sleek-based methods where you have this local embedding. So it's not clear if you can use, if you can say anything interesting about these embedding-based methods for general metrics. So it'll be interesting to see how we can actually use these directly use these loss functions in that framework and say something statistically interesting. And so this is the sort of final summary. So one is that I think from the morning we have had several talks, including Manik's and Scott's in the last but one talk. So it's good to use the evaluation metric that you care about or the performance metric you care about while you actually learn the algorithm, while you actually learn the model. And what we have is a flexible approach that sort of caters to a large metrics, but then it's just the, I believe it's just the first step. So it's just being sort of initiated, I would think, to bridge this gap between theory and what you really care about in the deployment scenarios. Thank you.
So any question?
Thank you. So if I understand correctly, you had one optimization problem, but then you left one parameter to be optimized for just one-dimensional optimization for the. So I'm asking, how are these two optimizations? I mean, are they? Do they work together well? I mean, how compatible are they? The choice of the first optimization, I mean.
Right. So I think it helps to draw an analogy to binary classification here. So in the binary classification, what you essentially do is, so let's say if you can actually have an estimate of your label being one condition on the features X. So if you have an estimate of P of Y equals 1 given X, then you essentially have, you can sort of use that to convert that into a label. For example, I can then, let's say, if you care only about 0-1 loss, then I can just threshold it at half, and I have a very consistent method in the sense that I know that this is the right thing to do. If you, let's say, if you have a right model for P of Y equals 1 given X. So that's the sort of analogy here. So if your labels actually obeyed coming from this sort of linear model, in the sense that the way I sample these label preferences is that there is an underlying matrix on which the user features are applied, and then those entries actually determine how the users express their likes, then makes sense. In the sense that if you have a good model, I can replace that first step with a different step. If you have a better way of modeling P of Y equals Yij equals 1 given X, then you can plug and play. So the first step is essentially coming up with a good estimate of what the probabilities are, and the second step essentially is for the guarantees, in the sense that if you care about a metric, then the optimal must sort of have that property.
Thank you, Naga. Okay, let's thank the speaker.